So with that introduction, let's talk first of all about soil texture. If we were to define soil texture, we would say that the texture of a soil is the percentage composition of sand, silt, and clay-sized particles that occupy the mineral matter in the soil. In order to understand the sand, the silt, and the clay, each of these is broken into what is called a soil separate. So if we were talking about only the sand, or only the silt-sized particles, or only the clay-sized particles, these would be called soil separates. If we were to look first of all at the sand separate, this would include particles from 0.05 millimeters in terms of effective diameter up through and including 2.0 millimeters. So from 0.05 to 2.0 millimeters, these size of soil mineral particles would be considered sand. The next soil separate, the silt, includes particles with an effective diameter of from 0.002 up through 0.05 millimeters in terms of effective diameter. I think you can see that particles that are in the smaller end of the silt size range are much, much smaller than those that are even in the bottom end of the sand size particles. So once again, from 0.002, that's 2/1000ths of a millimeter in terms of effective diameter up through 0.05 or 5/100ths of a millimeter. Those particles would be considered the silt separate. Anything less than 0.0002 or 2/1000ths of a millimeter in terms of effective diameter, it would fall into the clay separate of the soil. So once again, we have the clay from 0.002 on down or smaller, silt from 0.002 up through 0.05, and then from 0.05 to 2.0 millimeters in effective diameter, we have the sand-sized particles. Now, I've used a term there that I really haven't explained, and that term is effective diameter. I think you can visualize that not all of the mineral particles in the soil are going to be perfectly round little spheres. So if we're talking about an effective diameter, we're talking about take into consideration the actual size that this particle will occupy in the mineral fraction of the soil. The size of the particle, of course, in one dimension would be smaller than it might be in another. So they're not perfectly round little spheres, but collectively they do act similar to round spheres in the soil, meaning that each particle occupies an effective diameter. There are different ways in which we can determine what amount of the soil particles, the mineral particles, are in the sand separate versus the silt versus the clay separate. A very simple technique that you can use at home is to take the soil, air dry it, be sure you crush all of the clods or aggregates that are in this soil, and then with a flocculating agent, now in the lab we're going to use sodium hexametaphosphate, but if you don't have that, a small amount of detergent will work, just a small portion of a drop. If you get too much, it gets very sudsy and foamy on you. You place a quantity of this soil into just a fruit jar, add water, and totally, shake it up and suspend all of the soil particles. Now, why use a detergent, or as in the case of the lab, we use a sodium hexametaphosphate? Well, we're using that material because soil particles naturally want to attract to each other. Now, we've learned earlier that the particle surface on mineral particles has a negative charge. However, there are going to be cations in the soil which fit in between these negatively charged particles and help to cause these to flocculate or want to hold together. In order to get these soil particles to separate and settle independently of each other, we need to use what we call the dispersing or deflocculating agent. And that's the purpose of the sodium hexametaphosphate, which you'll see when you observe the laboratory tape on physical soil properties. So assuming that you don't have sodium hexametaphosphate sitting around in your kitchen counter, a small amount of laundry detergent, not laundry detergent, but dish soap would be a logical substitute. What that will do is it will get in there, it will help break these soil particles apart, it will help them not to want to cling together, and that allows them to settle separately from each other. So once you've placed this drop of dish detergent and your soil and your water into the jar, shake it up, set it aside, and let this set for at least overnight. And when you come back, what you'll notice is you'll notice a separation of the sand, which of course larger particles will settle faster. The silt-sized particles will be on top of the sand. And then finally the clay-sized particles. Most of those will have settled out overnight, but realize some of the smaller sized clay particles would take, even in a fruit jar like this with static water situation, up to 48 hours to settle out of that water. But the water will not appear clear on top. It will still have a little bit of cloudiness or off color to it. That tells you that there's a small amount of clay yet to settle out. So what you'll observe in this, what I call the fruit jar method then, is going to be an approximation of the amount of sand, silt, and clay in that particular soil. Now obviously in a soils testing laboratory, we don't utilize a fruit jar and we don't utilize dish soap or detergent. So in the laboratory unit, or laboratory portion of this unit, you will be using, as I mentioned, the dispersing agent, the sodium hexametaphosphate. You will be utilizing a known weight of soil, approximately 100 grams. You will be putting this onto a soil dispersing mixer. Looks very much like the old-fashioned metal cup milkshake mixers. You'll be mixing this soil with a given quantity of water for a period of time. You'll put this into a soil cylinder, and that soil cylinder is going to allow for the settling out of these soil particles. But rather than looking at the amount of sand, silt, and clay and getting an approximate proportion, you're going to be utilizing a hydrometer, a soil hydrometer. And the purpose of that hydrometer will be to measure the changes that occur in the density of that suspension over a period of time. And of course, the sand settles out in 42 seconds, the silt in about 2.5 hours, and then that remaining in suspension at the end of that 2.5 hours will be considered clay-sized particles. And as we measure the change in density, we will get some numbers that we will plug into a formula, and this will give us the actual percentages of sand, silt, and clay-sized particles in that soil. Why would we want to know what percentage of sand, silt, and clay-sized particles are in that soil? Well, we're going to want to know that because that will allow us to take that information and go to the textural triangle.